Under Uncertainty by Boris Aronov, John Iacono, and Khadija Sheikhan.
Yeah.
And Khadija will give the talk.
Hi, I'm Khadija. I'm going to talk about nearest neighbor searching under uncertainty, and it's a joint work with Boris Aronov and John Iacono. To start, I'm going to give you the motivation behind this problem. Suppose you are managing a 911 call center. You have a call from some location and you want to assign an ambulance to go there and help them. So what should we do? We should assign the closest one. But when uncertainty happens, you are not sure where each ambulance is. So for each one, you may have a region that you know that the ambulance is somewhere there. The approach here is you want the worst case scenario. You want to consider the worst case scenario. What if the ambulance is, for example, here? Which one is now the closest one? And you want to minimize the maximum distance, so you will assign this green one. But what if even the query, the person that is calling, has an uncertain location? For example, it could be due to GPS, or for example, each ambulance has some area to be at. So even in this case, we assume the worst outcome. So we want to assign an ambulance that has the minimum distance, even in the worst case scenario. Okay. This is the formal definition. You are given a set of uncertain sites, P1 to Pn, and you want to preprocess them, create a data structure so that given an uncertain query, you can return the nearest neighbor in an efficiently. In our case, we assume that these uncertain sites are discrete sets. For example, here we have P1, P2, and P3. Each one have finite number of possible locations, and distance is and also the query is a finite set, and we want to, the points are in general position, and we want to minimize the distance between the two farthest points. So, these three are distances from three sets, and P2 is the closest site, I guess. The related work, most of the works are either with uncertain queries or uncertain sites. For example, there are different approaches with uncertain sites, and some of them want to minimize the expected distance. The sites are not just some points. Sometimes there are regions with probability distributions, so you want the site that minimizes the expected distance. Or you want the one that has the maximum probability of being the nearest neighbor, or like the one we are interested in, you want the site that minimizes the worst case distance. There are also some other works called aggregate queries or group queries, where query is a set of points and you want to and distance from a site is an aggregate function of distance of each point in the query from that site. It could be average of all the distances, or as we said, the maximum of all distances. For example, here again, P2 is the closest to the query queue. The only work that has uncertainty for both queries and sites is probabilistic group nearest neighbor queries in uncertain databases. But in this one, sites are regions with probability distributions, but the query is discrete. Most of the works with uncertainty are just using heuristics. There is no worst case analysis, and there is no runtime guarantee. So you may end up looking at all the sites and computing the distance. They have 3 steps. They build a data structure like R trees. They do pruning, and then they end up with a set of possible nearest neighbors, and they compute the distance and choose the real closest one. Okay, our results. We first start with an approximate nearest neighbor. You have a query which is a set. What if we want to represent it with only one point? An idea is just pick an arbitrary point in Q. For example, if you care about the average of the distances, maybe centroid of Q is a good example. Or if like us, you are using the maximum distance, center of Q, the minimum enclosing circle may be a good idea. We proved that even when sites are uncertain, center of the minimum enclosing circle is a good representation of the query. We proved that if, for example, P is the closest to the center, P star is the real closest site, distance of the whole query from that site cannot be more than square root 2 times the distance to the real closest site. Okay, so P is the closest to the center of the query, and P star is the real closest one, and distance of Q from P is less than square root 2 times distance of P star from Q. This was proved before for where sites are certain, but it's also true for uncertain sites. So how that can help? It's much easier to find the closest site to a certain point. We all know about the Voronoi diagrams. You have a set of points, draw the Voronoi diagram, and do a point location in it to find the closest to that point. So if sites are uncertain, ideally we can draw their Voronoi diagram. The distance is equivalent of the Hausdorff distance, the distance that we are using. And there are lots of works on Hausdorff-Voronoi diagrams. If the sites are disjoint, for example, you can do it very nicely in polylogarithmic time, in very fast. Okay. The next result is nearest neighbor under uncertainty, but using L infinity metric. This problem definition is the same. You are given a set of sites and a query and distance, but the distance between any 2 points is defined by the L infinity metric. You can see here, for example, distance between P and Q is the maximum of their x distance and y distance. So here it's their x distance. Okay, and we want to pre-process them so to answer these queries efficiently. First, we do an observation. If you are given 2 sets and you want their distance, their L infinity distance, the only thing you care about is their bounding axis parallel bounding box. You can compute the distance without knowing where exactly the dots are, just knowing their bounding box. So how does that help? From now on, we don't care how many points there are in each uncertain set. We only care about their bounding box, and the size of the problem is reduced to the size of the number of sites, not points in them. Okay. We define some properties of a rectangle query. It has a center, it has width, height, delta x and delta y, and we define delta to be the absolute difference between the width and the height. Okay, and from now we assume that delta x is greater than delta y. I mean that the rectangle is horizontal. Okay, and if it's vertical, you should replace every left and right with up and down in the next slides. Okay. This big rectangle is our query. Every site that its center is to the right of this O, we only care about its right edge to compute the distance. Every site in the left, we only care about their left edge. So we divide sites into 2 sets, P left and P right. Okay. We search for the nearest neighbor separately in each of these sets, and then compare them to find the real nearest neighbor. Okay. Now, the problem is reduced to finding the nearest neighbor of a query rectangle, nearest segment, vertical segment to a query rectangle, right? Okay. These are the segments left from PR, from the right rectangles. And Q, this rectangle is our query. If you look at distance definition, what we care about is distance from this corner, for example, from points here. Okay, so the distance is distance from the center plus x distance from the center from plus delta x over 2, and again y distance from the center plus delta y over 2. If we shift the center to the left by delta over 2, delta was the absolute difference between x distance and y distance, between width and height. Okay, so distance from any point in PR from the query is the same as distance from this point plus some value delta y over 2, which is the same for all the segments. Okay, so instead of querying with a rectangle, we can query with this point, O sub r. Okay. But how can we find the nearest segment to a certain point? Again, it's Hausdorff distance. Segments are disjoint because we had general position, and it satisfies axioms of abstract Voronoi diagrams. So we can do it in we can construct the point location structure in n log n time using linear space, and in the queries we can answer in log n time. Okay, so the problem here is based on where your query is, the set of segments that you want to look at is different. Okay, you want to look at the segment, the left edge or right edge of those rectangles whose center are to the left of your query center, right? Okay, so what's the idea? Just sort all of the rectangles based on the position of their center. Then for the right segments, for example, pre-compute the Voronoi diagram for each suffix of these sites, Sort them for each suffix of these sets, pre-compute the Voronoi diagram of their right segments. Okay, and repeat this for the left segments too. In this way, you will build n Voronoi diagrams. Each has n log n size, so each takes linear space, so quadratic space. Each one takes n log n time to build, so n squared log n expected pre-processing time. Sorry, it's expected because this abstract Voronoi diagram thing, it has expected in its time. So it's here. And okay. Can't we be a little bit smarter? Instead of storing all the Voronoi diagrams for all the suffixes, what can we do? We can build a binary tree. Okay, after sorting them by the center, build the Voronoi divide them into two sets, left and right. Okay. Compute the Voronoi diagram for any suffix of its children. For example, for the root, compute the Voronoi diagram of the right half and all of them together. Okay, 2 of them. Okay, so when we do a query, we will follow the path in this binary tree. We will end up with log n nodes. We need the Voronoi diagram of these log n nodes, right? And we will end up with log n nodes. Each takes log n time to do the query in it, and the size is n log n space and n log squared expected pre-processing time. But instead of binary, we can use m-array trees. Sort the sites, divide them into m sets, compute the Voronoi diagram for the first 1, first 2, first 3, first 4 sets. Okay, and then when we do a query, we will end up with log n base m points on the path to the leaf, and we will do a query in each of these diagrams, and that's it. This plus s here is the time for computing the bounding boxes. The s is the total number of side points. We had after computing the bounding boxes, we don't care about this s anymore. And if we replace n by n to 1 over delta, we'll get these runtimes. Okay, this is the only work that's been done with worst case analysis, and but this is only in L infinity, and we don't know if if for L2 there is a polylogarithmic algorithm with which looks at less than linear number of sites and gives the exact answer. Thank you. Any questions?